You ready? Okay, so lesson 49. We've seen logarithms. We know that logarithms of a number is the same as the exponent, right? Now we're going to look at their graphs. And it's important because the data that you have, notice you say that this is the same graph, but it's not. And why is it different? This one has n here, and n is the answer to an exponent, to a base to an exponent. Whereas here, L is the exponent, okay? Because it's the logarithm of a number. Notice that I use the same base for both so that you can see the difference. And let's plot it. It's not going to be exact, because if you notice, for -3, I get 0.001. And for -2, I get 0.01, which is really far away. And for -1.1, for 0, I get 1. For 110, and then 100. So the scale, I had to make it so that it was, it started at 100. So in the beginning, you're not really going to notice the big difference. So for -3, it's almost 0, right? Almost, but not quite. For -2, it's almost 0 also, but a little bit larger. For -1, it's 0.1, so again, almost 0 at this scale. For 0, it's 1. Again, you won't notice it at this scale. But for 1, it's 10. So it starts going up a little bit. For 2, then we get it. And for 3, it goes all the way up to 1,000. So if and this is something that we could have expected because this is an exponential equation. And we've seen that exponential equations, just like the mice in Australia, they completely explode, right? It reproduces really, really high. Let's see if this grows this far. With this one, when x, or when n, because n is here, so in the x-axis, in the horizontal axis, when n is 0.001, obviously you're finding an exponent. So when it's almost 0, you get -3. So it's all the way down here. When it's you get -2 when it's -1 here. At 1, we get 0, right? Up here. And then it jumps up to when it's 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know, when it's 10, my bad. When it's 10, it's here. When it's 10, it's 1, right? No, when it's lost. When it's 1, it's 0, so it's here. When it's 10, it's 1. And then when it's 2, it's 100. And when it's 3, when it's 1,000, so it's down here, it's 3. So what do you see happening? You don't see the difference? You still think it's the same graph?
No.
Completely different. That one grows on the x-axis, on the horizontal axis, whereas this one grows on the vertical axis. This one, even though this one's not going to grow flat, is it? It's still going to grow just a little bit, but the amount of growth it does is really small compared to the distance it grows, right? Whereas this one, it's the height that goes up. So it's the same shape if you want to look at it, but it's like 90-degree. It's flipped 90 degrees. I just want you to understand, and I think Joanna saw it immediately when she, without using the calculator, she knew that the result was going to be the same thing that we have here because these were the exponents that we were putting. And again, this just shows you that logarithms are nothing but exponents, right? Because that's what you got on this side, okay? So that's what I want to explain here. Next, because these two are intimately related, may I erase? you can conclude, you can see it on the video, that's the whole point. That, do you remember my infamous chart that when you multiply, what do you do to the exponents?
You add them.
And when you divide,
You subtract.
and when you raise,
You multiply.
multiply. Since we're looking at logarithms, now it's going to be backwards. So, if we have logarithm, assuming it's the same base, but in this case it's going to be base 10. Logarithm of m plus logarithm of n, these are added, right? And you remember that both of these represent exponents, don't they? These are exponents that you're putting here. So if you're adding exponents, what does it mean that you were doing what operation were you doing?
Multiplying.
You were multiplying. So this is the same as saying logarithm of, right? Does that make sense? Same token. If you are subtracting, what is it that you were doing before?
Divide.
You were dividing. So you've got logarithm, right?
Yes.
And if you have a multiplication, because the n is multiplying this, what were you doing? Raising. So you have, okay? So these are rules for logarithms. Okay? So they're going to ask you to develop it. How do you develop it? Did you understand? Does this make sense? Okay. So how do you develop it? You know that m equals b to the a and n equals b to the c. Notice that you have the same base. If you don't have the same base, that doesn't apply. And you know that from this logarithm base b of m equals a and logarithm base b of n equals c, right? So if you have to prove that those are the same, how would you go about it? Logarithm base b of mn equals, and you substitute the m and the n for what you have up here, which would be logarithm base b of ba times b to the c, right? Does everybody agree?
Yes.
And that would be the same as logarithm b of b a plus c, because you copy the base and add the exponents, right? Yes? Logarithm base b of b, oh, this is the same as a plus c logarithm base b of b. Logarithm base b of b is 1. And that gives you a plus c. Do you agree? And what is a? A is logarithm base b of n, and c is logarithm base b of n. And I have proven that this is the same as this. Isn't that cool? Just by substituting.
Seriously?
Seriously. You can do the exact same thing with division, at least, okay? Is that clear?
More, please.
And that's it.